And now, here's Dr. Locke.
Thank you, Renee, for that kind introduction. So in today's webinar, I'd like to discuss and highlight why we should move away from ether extract and measure fatty acid concentration and profile of feedstuffs, emphasize the considerable variation in the fatty acid concentration and profile of different feeds, and then demonstrate why this may be important with respect to diet formulation, and then finally highlight possible effects of free versus esterified fatty acid in feeds and possible impacts this may have on rumen function and animal performance. So firstly, I'd like to revisit a topic first discussed by Dr. Jenkins in one of the earlier webinars in this series, that being looking at ether extraction and what does ether extraction really mean. Now it's important to remember that ether extraction doesn't just measure glycerol-based compounds such as triglycerides and compound lipids such as phospholipids and glycolipids, but it also measures non-glycerol-based lipid-based compounds such as waxes and alkanes. Now this is important because when we're discussing fatty acid or interested in lipid content of feeds, what we're really interested in is the fatty acid concentration of feeds, because it's these fatty acids that supply energy to the cow, that have effects on different tissues based on the different fatty acids, and then have effects on rumen bacteria and can potentially have effects on rumen function. So it's really the fatty acid concentration and the fatty acid profile of feeds that we're mostly or really interested in. And this is important because, especially for forages, they can contain a wide range of different waxes and alkanes, for example. So in a typical ether extract of a forage, less than 50% of that ether extract is going to be representative or represented by fatty acids. Whereas in concentrates, or in different concentrates, about 80% of that ether extract is going to be represented by fatty acids. So NRC equation in 2001 explained this as total fatty acids equals ether extract minus 1. But as we can see from these two examples here, that's really not universal across different feedstuffs, and there's really no good equation or relationship between total fatty acid content of a feed and the amount of ether extract present in that feed. And it's for those reasons that we feel it's important as we move forward for ration formulation and balancing that we look at measuring and determining total fatty acid concentration of feed rather than ether extraction. So in this next slide, I simply wanted to remind everyone of the wide variation there is in total fatty acid concentration of feedstuffs for the different feeds available for diet formulation. From those feeds that contain very, very low levels of total fatty acids, for example, different forages containing less than 5% fatty acids, to those feedstuffs that go all the way up to 80 to 100% fatty acids, such as different commercial rumen fat supplements that are very high in fatty acids. There's this wide variation. And then also I wanted to remind everyone that there's in nearly most common situations there's 5 fatty acids that account for most of the fatty acids present in a dairy cow ration. This being our saturated fatty acids, palmitic acid and stearic acid. Oleic acid, our primary monounsaturated fatty acid, and then our primary polyunsaturated fatty acid in dairy cow rations being linoleic acid and linolenic acid. And then what also I wanted to remind everyone of here is that depending on what type of feedstuff's being fed, these different feeds will contain different profiles of fatty acids. So in our grass-based forages, it's linolenic acid, 18-3, which is the primary fatty acid present, typically around 50% fat of linolenic acid. Whereas in our corn, soy, cotton seed-based products, linoleic acid is the primary fatty acid present, followed by oleic acid being the second most major fatty acid. So there's these differences in different types of feedstuffs. However, what's important to remember that any corn-based product, for example, whether it's corn silage or distiller's grains or even corn oil, the profile of those different corn-based products are all going to be fairly similar because they're all starting from the same corn lipid material, primarily being corn oil. So linoleic acid is going to be the most predominant fatty acid, for example, in all corn-based products. So now moving into some examples of different feedstuffs, I wanted to start off here looking at distillers grains. This is some analysis we did a few years ago now, looking at 20 different samples that were sent to us from a commercial lab, looking at total fatty acid concentration and fatty acid profile. In this example, total fatty acid concentration ranged from 10 to 18% dry matter, so a large variation. And then also in the figure here, showing our 5 major fatty acids, as I highlighted in the previous table, and then the composition of the distillers grains here. Obviously, distillers grains in this case is corn-based, so linoleic acid is the primary fatty acid, accounting for about 50-55% of the fatty acids in these distiller samples. And then the last thing I wanted to point out here is if you look at these very small error bars shown in white here, I just circled a couple of them. Across these 20 samples, even though there is a wide variation in total fatty acid concentration, 10 to 18% dry matter, there is very little variation in fatty acid profile of these distillers. So I think based on this and similar analysis from other feedstuffs, having accurate values for total fatty acid concentration of these feeds, it appears to be much more important than having analysis back on fatty acid profile. Second example I wanted to look at was tallow, and in this case I just wanted to highlight from some recent analysis we've done that remind people that tallow is really not just a saturated fat source. In the examples we've recently had come back, tallow only represented was represented by about 50% by saturated fatty acids, so primarily palmitic and stearic acid, whereas about 40% of the fatty acid present in tallow are monounsaturated, primarily oleic acid, with a small amount of polyunsaturates, and then some amount of trans fatty acids, which represented a wide range in number of individual fatty acids present in very small concentrations, many of which we don't know what biological effects that they may have. And then finally, we recently saw some commercial analysis of tallows, where it came back saying that those tallows contain 10 to 16% linoleic acid, which would be a concern if we're not knowing what accurate values we have for that specific tallow, for example, that we may be feeding. So that's very high levels of polyunsaturated fatty acid in tallow. So now moving forward to look at variability in the fatty acid concentration in forages. This is some data from the Netherlands that came out earlier this year, looking at both grass silage and corn silage, a large number of samples in both, and looking at the mean and then the minimum and maximum values for these different forages. And in both cases they saw about a 2 to 3-fold variation in total fatty acid concentration in grass and corn silages. And there's very limited data on some of these variabilities at present. We started to look at this last year, and we in this example I'm showing 45 corn silage samples from the 2011 corn harvest that we received early last year, that we measured for total fatty acid concentration, shown on the y-axis here as percent dry matter. And here I'm simply showing a frequency distribution plot to show the range in total fatty acid concentration of corn silage samples. The diamond here in the middle shows the mean or average fatty acid concentration, which was about 2.6% in this data set that we had. And in this blue box here, that shows the 75% of this results were within that range of about 2.4 to 2.7% fatty acids. What is of interest though is this wide variation we saw though in total fatty acid concentration, going from anywhere from about 1.8 all the way up to 3.2% of dry matter of fatty acids. So a wide range, again a 2 to 3-fold variation in total fatty acid concentration. Even though we saw a wide variation in total fatty acid, there was a very little or minimal variation in fatty acid profile across all of these corn silage samples. Next we looked at some different byproducts, in this case looking at canola meal, distillers grains and cottonseed. This plot showing using the same format. And for cottonseed we saw a variability of anywhere from 17 to 24% fatty acids at dry matter basis. For distillers grains, it's about 8 to 15%, so slightly less than the variability we saw in the previous data set for distillers I showed you. But most interesting was the canola meal here that ranged anywhere from less than 2% all the way up to about 19% fatty acids on the percent dry matter, so wide variation there. And across all of these there's still considerable variation. So next here I wanted to look at, take some of this variation that we're seeing and putting this into a diet formulation situation to see what impact these variations may have on total fatty acid concentration of the diet and intake. So here just taking a diet we've recently fed in one of our studies, very simple diet, no added fat sources in this diet, formulated for about 90 pounds of milk, 55 pounds of intake. And in this case, total fatty acids concentration in the diet was 2.9% and with about 1.6 pounds of fatty acids intake. What I did calculate out here in this last column here is the contribution of each of these different ingredients to overall fatty acid intake based on this diet formulation. And what you will note here is that our corn silage has contributed nearly 30% of total fatty acids coming into this diet, or being supplied by this diet. The major one being cottonseed supplied 34% of the fatty acids, and then our corn grain, in this case high moisture corn, supplied 17% of the fatty acids in this sample. So here is the book values that we had listed in our diet formulation package for these different feed ingredients. So in this next slide I wanted to take what this would be if we use some of the variability that we were seeing in our survey that we just showed you on the data. Now in the opening example, fatty acid concentration of corn silage was 2.2%. However, in some of our survey work, we were seeing corn silages coming back as high as 3.2%. And in that example, that would increase fatty acid concentration in the diet from 2.9 to 3.3%, with a 15% overall increase in fatty acid intake. Now, our next example here would be what if there had kind of been a perfect storm in changes in fatty acid concentration of feeds. So here I've locked in that higher level of fatty acid concentration of the corn silage at 3.2%, and then just showing here now what would happen if we had higher levels of fatty acids in both the cottonseed and in the high moisture corn grain that we were looking at. So for cottonseed there was 18% fatty acids, and in our survey work we were seeing anywhere up to 24%. And for high moisture corn it was locked in at 3.3%, and in some very recent analysis we were seeing some high moisture corns coming back at about 4.5%. So you can see this has a quite considerable impact on total fatty acid concentration, going from 2.9 now up to 3.75%, and taking increasing total fatty acid intake to 2.1 pounds per day. This is actually the equivalent of a 30% increase in fatty acid intake, or approximately half, 0.5 pounds of fatty acid increase per day. So just by having some slight differences in the concentration of fatty acid in some of these key feed ingredients, it can actually have quite big differences in the overall fatty acid intake that we may not account for if we do not have accurate data on fatty acid concentration of these ingredients. So moving on from just looking at total fatty acid concentration, I wanted to now just look at what type of fatty acids are present in feeds, whether there is esterified lipids, as triglycerides, phospholipids, glycolipids, or just as free fatty acids. And the interest here is coming from some data that's shown that plant lipases release free fatty acids either after cutting or during ensiling of forages. And this is highlighted quite nicely in this data set here from Europe. We're looking at some different grass varieties either in the fresh form or in the ensiled form, and then looking at the proportion of free fatty acids as a percentage of total lipid. And we see these big jump ups going anywhere from 2 now up to over anywhere from 27 to 70% in ensiled forages. So there is evidence that we can get release of fatty acids from the esterified form into the free form. So we wanted to look at that further in some of our data sets. And the first one I'm showing here is the corn silage samples that I showed earlier on. This is the same data set, but now looking at the fatty acids in each fraction, and the fractions we've listed out here is esterified fatty acids, which is going to be primarily triglycerides, or as free fatty acids. And in this case, for across these 45 samples, we saw anywhere from 15 to 30% of the fatty acids in those corn silage samples being in the free fatty acid form. So quite a large variation in the amount of free fatty acids present in these corn silages. While there's a large variation there is very little difference in the fatty acid profile of these different fractions, other than higher levels of linolenic acid in the free fatty acid fraction that we wish to look at further in the future. Also looked at this in our byproduct feeds. Here on the left is the figure I showed for fatty acid concentration previously. And now here on the right, looking at the percent of free fatty acids in as a percent of total fatty acids in these feeds. And we can see in this case that cottonseed, that all of these feeds have a significant amount of free fatty acids in them, with much less variation in the amount of free fatty acid in the distillers. But the major one that jumped out at us in this analysis was that the amount of free fatty acids in canola milk was anywhere from less than 2% all the way up to 30%, of the fatty acids present in canola milk. So again, wide variations and differences in the amount of free fatty acids in these byproducts as well. Now, why is this potentially of interest to us, the amount of free versus esterified fatty acids in feeds? And really it comes down to rumen lipid metabolism and the fact that hydrolysis, or the release of fatty acids from the glycerol backbone in esterified lipids, is an absolute prerequisite for biohydrogenation. Bacteria, in order to biohydrogenate, so to convert unsaturated fatty acids to saturated fatty acids, have to have the carboxyl end of the fatty acid, the COOH end of the fatty acids. That's an absolute requirement for biohydrogenation to occur. So the quicker or the more free fatty acids released into the rumen at any one time, the more quickly or faster the bacteria have to detoxify or biohydrogenate those fatty acids. Now, there's very limited data on how this may impact biohydrogenation, but here just showing some in vitro data from a number of years ago now, either looking at free linoleic acid added into the in vitro culture system or esterified linoleic acid entered into this culture system. And as you can see here, very quickly with the free fatty acids, there's a large amount of linoleic acid shown in blue here that has to be biohydrogenated because it's already in the free fatty acid form. Whereas with the esterified lipid, there's a slow hydrolysis and release of that linoleic acid that then has to be biohydrogenated or detoxified. Now, if we now look in this slide, looking at the key biohydrogenation intermediates, our CLA isomers and our trans 18-1 isomers. And we can see that when we have the free linoleic acid added into the rumen, as I showed in the previous slide, there's a lot of linoleic acid that needs biohydrogenating quickly, that we now have this large increase in the amount of these biohydrogenation intermediates being produced very rapidly in the rumen, whereas with the esterified lipid, we've got this much lower level and much steadier accumulation of these intermediates. And it's this larger accumulation here of these intermediates that's going to potentially have much greater impacts on the amount of intermediates or negative biohydrogenation intermediates leaving the rumen that may subsequently impact, for example, milk fat depression. So there's one in vivo study to support that data, and this is looking at the amount of free fatty acids in cottonseed. And here there's this study fed 14% cottonseed in the diet with one of three different cottonseeds, or a control cottonseed with low level of free fatty acid, or two cottonseed samples that had much higher, about 20-25% free fatty acids in the cottonseed. And in this case, the only difference being here is that the amount of free fatty acids in the cottonseed, but as you can see here, we get this much lower accumulation of milk fat in these diets that had the high free fatty acid cottonseed present, to supporting this concept that the amount of free fatty acids present in these cottonseed samples may be negatively impacting biohydrogenation and increasing the amount of negative biohydrogenation intermediates that are responsible for causing low milk fat. So to summarize, ether extraction includes fatty acids plus other non-lipid compounds, and it's a fatty acid that's the nutritional currency that we're interested in. Considerable variation in total fatty acid concentration of corn silage and other feedstuffs, and this variation is not accounted for in book values. Such changes in variation in fatty acid concentration may impact total fatty acid intake and the effect of fatty acids on rumen function and animal performance. And there is a significant and variable proportion of fatty acids in corn silage and other feeds that's in the form of free fatty acids. And limited results do support the concept that free fatty acids may negatively impact rumen biohydrogenation to a greater extent when compared with esterified fatty acids. So hopefully some take-home messages here is that the fatty acid concentration of individual feedstuffs is variable. Accurate characterization of feeds may help improve diet formulations. And I think this variability in fatty acid concentration of important feedstuffs may explain some of the variations or issues that we may see on farm with trying to troubleshoot some of these such issues. And fatty acid analysis of feeds is becoming more widely available, but of course it's still fairly costly. So with that, I would like to thank you for your attention. I hope that provided some useful information for you here. I'd like to hand it back to you now, Renee, and take any questions as are available. So thank you very much.